If you've ever broken open a toy, chances are you've already seen springs. They're used in industrial machinery, vehicle suspension, mattresses, and so many more things. But how do they work? And what is it about them that makes them so useful? First, we need to understand exactly what a spring is. A spring is basically a conjunction, a magical thingamajig that it's a device that when you apply a force to it, it changes its shape. And then when you remove the force, it goes back to its original shape. And this is called elasticity. Now, not all materials are elastic. Some materials like clay can change their shape permanently when a force is applied to them. And this is what we call plasticity. Now we can measure how much a spring is changing by measuring its extension or compression, where extension is the increase in length of a spring and compression is the decrease in length of a spring. Now all of these changes in the state of the spring come when a force is applied to it, and we can measure that force by using a device called a Newton meter. Now we can measure how much a spring is changing by measuring its extension or compression, where extension is the increase in length of a spring and compression is the decrease in length of a spring. Now all of these changes in the state of the spring come when a force is applied to it, and we can measure that force by using a device called a Newton meter. Now if we're using an elastic spring, we'll see that the graph is a straight line that's passing through the origin, which means that there is a linear relationship between the force and the extension of the spring. That is, if we double the force, we double the extension. If we halve the force, we halve the extension. And if we remove the force completely, the spring will return to its original length. Now this linear relationship is described by Hooke's law for springs, which states that force equals to spring constant into extension. Now you may be thinking, what is this spring constant, or what is this K? Well, think of it as a measure of how stiff or flexible a spring is. A stiff spring has a high value of K and requires a larger force to stretch or compress it. A flexible string has a low value of K and requires a small force to stretch or compress it. Now it's important to note that this is not a universal constant. The spring constant can vary from one spring to another. So usually, you'll have to calculate it for each spring separately. Let's try this with an example. Let's say we have a vertical spring fixed from the top end with an unstretched length of 300 millimeters. You attach a weight of 5 newtons and its length increases to 385 millimeters. What do you think would be the spring constant here? And then let's say you switch out the weights to an 8 newton one. What's the length of the spring now? Well, according to Hooke's law, the length of movement and force applied are directly proportional. So assuming that the elastic limit has not been crossed, we can use the formula F equals to Kx to determine the spring constant. For this spring, we can simply plug in the values 5 newtons and 85 millimeters to calculate the spring constant as the missing figure. And that comes out to be 59 newtons per meter. This means that if the spring constant was higher, it would take more force to expand the string by the same amount, which means the spring would be stiffer. Similarly, if the spring constant was lower, it would take less force to expand the spring by the same amount, making the spring more flexible. Alright, we know the spring constant for this particular spring now. Now it's a simple game of plugging in the right values into the spring equation to figure out how much it would extend when an 8 newton weight is hung on the spring. Once we do that, we'll know that it stretches by 0.136 meters or 136 millimeters. But that's just the extension, and we need the total length. So we're going to add 136 to 300 millimeters, and that's the net length, which is 436 millimeters with the 8 newton weight hung on it. Now by now you should know that I don't like keeping things simple, and neither does CIE. Well, yeah, it's a problem. But how do we plan on making this more complicated? Well, what if this force was applied to more than one spring at the same time? Well, Hooke's law remains the same. What changes is how the weight acts on the springs. For example, if we apply a force on two springs in parallel, the weight will distribute between the two springs so that they stretch under the combined effect of that force. And I know that's a weird and unnecessarily complicated sentence, so let's simplify it. What it means is that the net weight of the object will divide and balance over the two springs. So spring P receives part of the force, Fp, and spring Q receives another part of the force, Fq. And we're going to represent each force with Hooke's law's equations for each spring separately. Now bear with me. Things are about to complicate just a bit more now. Since the weight is balanced between the two springs, both springs will extend by the same amount, which means that the total combined weight of the two springs can be expressed by the sum of the forces acting on them. So you can say that the effective spring constant of two springs in parallel is going to be the sum of their individual spring constants. And in essence, this applies to any number of springs as long as they're attached in a parallel setup. The effective spring constant will always be the sum of their individual spring constants. But here's where things differ. They're different when springs are attached in series, where two or more springs carry the same force through each other. In this case, each spring will extend under the weight of the same force. Let's call it W. The total extension of the springs will be the sum of the individual extension of each spring. So the total extension is basically the extension of spring P plus the extension of spring Q. So the effective spring constant will be this. Let's recap. If you put springs in parallel, it will increase their effective spring constant and reduce how much the spring stretches when a force is applied. If you put them in series, it will reduce their effective spring constant and increase how much the spring stretches in total. Now, springs aren't infinitely stretchy. So what happens when we move beyond the elastic limit of a spring? How does it impact the spring's performance? We'll be talking about this and a lot more in the next unit. So stay with us.